Yeah, thank you, David, Alex, for inviting me, and I want to congratulate you for the successful Brain project and the subsequent U24. Yeah, so yeah, you heard already. We're really pushing the resolution and the spatial temporal resolution for both and the basal. And now, especially with David's new scanner, I think we're pushing to some really, I think probably 400 or even 200 microns at that range. But as Renzo's here, Renzo has pointed out many years ago, I think we try to always get the Holy Grail to try to visualize CMRO2, which is more related to neuroactivity, and currently available to us, three hemodynamic parameters, CBF, CBV, and BOLT. I would say borrow Renzo's metaphor. I would say you guys are all in Porsches. The ASL is more like in the bicycle. But it has advantages, as you can see. Yeah. So CBF is more quantitative, more specific, but less available. So yeah. Um, Yeah, so it's been like an uphill battle for ASL. It's been, I would say, more than 20 years. When I was a fellow at UPenn, the 70 come out, and it was considered one of the killer applications, ASL, because it has dual benefit. It has, high SNR, which is super linear right now. And also, the T1 increase with field strength. So when you look at, improve from 3T to 70, you're looking at more than 3 or even 5-fold SNR gain. Yeah, so the challenges, of course, there are many challenges, B0, B1, inhomogeneity, especially B1. It goes down even half, even 30% at the labeling region. So it has been a really challenge for us. Yeah, so on top of that, you have the SAR, you have the T2 star effects and the coil coverage. So just to yeah, keep long story short, my lab has been working on this past 10 years. USC got the first para actually in North America in 2017. So it's been almost 10 years. So we've painstakingly tried to optimize many parameters. One is, of course, labeling. We try to make the label robust to B0, B1 inhomogeneity. And I'll still keep the whole brain coverage. Of course, also another thing is we use this background suppression pulse, which is basically adiabatic pulse. You have to be careful, which if you use 3T pulse, you will end up losing almost 1/3 of the signal. So everything has to be optimized. Eventually we use. One is called worst. The other one is called the Optim. It's a custom optimized adiabatic pulse. And also readout. We initially were doing the TFL, which is more like MP range. So we try to minimize distortion, minimize T2 star relaxation. As you can see, we can do 2 millimeter isotropic with some clinical case, so it's feasible to do it. It takes about 10 minutes. We've also given out to many sites, so it's applicable to other 70, of course here with David. So recently, what we've been really pushing is really try to push to the next level, try to do laminar, mesoscopic. So we're trying to push to isotropic 1 millimeter. So I have a very talented student, Cheng Zhao. So he just published that paper. So what we come up with is really a stack spiral. So this is, um, it's a spiral in plane, but in Z direction still facing encoding. But we kind of rotate the encoding angle, so you kind of improve the signal incoherence. So that's good for compressed sensing kind of reconstruction. Another good thing about the spiral is, of course, it's high efficiency, but also, it kind of reduce the saturation effects with the TFL, and also um, it started with the case-based sensor, so it's more resilient to motion. You can even do motion correction between the frames. So there's lots of variant you can do. For example, you can do dynamic reconstruction, so you can do FMI. Basically you can play with it. So we already heard that there's lots of challenges. For example, this is without correction, so which is pretty good. So you have to do trajectory correction. We're using GIRF. Here you can use the field camera, but then you also need to do the B0 correction. We use the multi-frequency imaging, which is more time-consuming. So we heard Kevin talk about many new cool stuff we may be able to implement. Yeah, and but anyway, yeah, we can do beautiful 1 millimeter whole grain perfusion on our system. You can compare. This is the top is the spiral. This is visit one, visit two on different slides. This is Cartesian built TFL. So it has 3 times SNR gain and 2 times repeatability gain. So which is very impressive. So working with David, so we were one of the pilot U24 projects. So you can see the red one is actually the next gen. So the dark line is our Terra. So because your through rate and the maximum gradient is 200, 900. So we are 80, 200. So you have about 3 times higher limit. So that will, but we didn't push to the maximum. But even that, uh, the results is you can either do faster, you can from 12 segments to 4 segments, so which means 3 times faster. Or another way is you can do 2 segments, so comparable to the Para, but you can almost double the flip angle, so you kind of increase the SNR. So yeah, basically or you can use the time to push resolution. So we pushed to 0.8, which is very impressive for green. Yeah, with the capability, you can do laminar analysis. Of course, you can unfold the cortex, and you can do deep, middle, superficial, and it's always higher in the middle, but there's subtle difference. For example, in the this is V1. This is V1. This is motor cortex. This is specimen. So you can see the M1 is more middle towards superficial, but the V1 was more deep layer. So this is the line of generic. So we know we know it has a dense strip there. And also you can look at across the cortex. This is the big brain atlas, which is the staining of cell body. So it's basically cellular density. So cellular density corresponding to energy demand and also basically perfusion. So that's we have very good correlation, which is nice. On top of that, you can also do functional MRI. So we started actually maybe 5 years ago. So we basically initially we used David's Zoom the Grace kind of idea. So you use Grace to cookie cut one region. So you can do high resolution within that region. This is the motor cortex. You can do 5 by 5 by 10 centimeter. And you can label above the circle of Willis. So you simultaneously label AC, MC, PC, which is the sweet spot in the 7T. It's high B1, good B0 homogeneity, and you can even use reduced free angle, reduced SAR, and also the transit time is much shorter, in this region. So here, we published in 2021. You can even do multi-delay, so you can fit the transit time. The transit time is shortest on pure surface, increase 100 milliseconds towards the middle and the deep layer. I think it's matching the model of John's model, and the perfusion, laminar profile is also very nice. It's matching the specimen. This is microvascular brain specimen. You can also do finger tapping, and then we can detect the, Renzo, the double peak. And here is the double peak. Yeah, so it disappears. The deep peak disappear when you do the finger brushing, which means you don't need to program your movement. You only receive your program. So both, of course, you see a little bump, but of course it's dominated by this venous gradient. Yeah, so. So the next step, we will really try to push the CMR2. So we basically try to measure CBF, CBV, CM both together. So this is the sequence we come up. It's combine a Picasso with single inversion pulse, so you can get ASL basal together, then you get another bolt. This is Grace, the Zoom, the 3D Grace. Yeah, so if you do finger tapping again, you would see this characteristic double peak in the omega kind of hand knob. This is CBF, this is both, this is vasal, vasal is negative. You also see the double peak. Okay, yeah. So so you also need a breathing test to calibrate. The nice thing is, you get this parameter also, they have a laminar profile, which means, they varies instead of, you use a fixed number. With this, you can actually, we use a very simple task with a ring stimulation. You can see the ring stimulation maps onto the visual cortex, but the center fovea is actually the negative one. So that's well known. So basically, we derive the laminar profile CBF across the eccentricity. So there is the negative bold. You can see actually negative bold was surprising the deep and the superficial layer, so which means they're top down, and you can see the CMR2. Very nice, if you see the correlation between CBF and the CMR2, that CBF shows the best correlation with CMR. So CBF is as close as you can get to CMR2. Of course, there's correlation between CBV and the bold, but it was a little bit more spread out. So recently, we actually have been using the spiral. So we have a full brain coverage. So again, we can detect the double peak. This is actually, we piloted a little bit with David. This is a working memory. We just want to show you the coverage. You have this frontal striatal network, positive activation, test positive, but you also have test negative, right, which is the default mode network, which is very central to neuroscience. The interesting thing is you have 3 times more data with the next gen. So actually next week, our group's gonna come again to collect more data, try to derive this very exciting study. Yeah, so we pilot a little bit. We can see simultaneous motor and visual, so both the negative basal and the positive ASL. derived CMO2. There's negative in ACC. So we're very much looking forward to it, to more data collaboration with David. Yeah, so that's my last slides. Just to show you now is with all the technology development, we're catching up with all the Porsches. Yeah, but still ISO 1. Yeah, I think with David's scanner, we can push to 7 millimeter right now. So just want to thank my lab. They're virtually online, especially Chen Yang, Xingfeng. They're very talented. And of course, David and Alex. Thank you.